This section is about predicting the polarity of molecules and understanding why some molecules are polar and others are nonpolar. We know the term polar describes a bond in which one atom has a partial positive charge and the other has a partial negative charge. Because most molecules have polar bonds, molecules as a whole can also be polar. In a polar molecule, electron density accumulates towards one side of the molecule, giving that side a partial negative charge and leaving the other side with an equal but positive partial charge. Now it depends on the molecular shape. We just were looking at one single polar bond. So if I looked at HCl, I would look at Cl's electronegativity number and H's electronegativity number, subtract the two, and if my difference was greater than 0.5, it is a polar bond. We would point an arrow towards my more negative atom. That would be slightly negative, and the other end, the butt end, would be slightly positive. But what if I have a compound like CO2? We've drawn CO2 now numerous times. We know it's a linear molecule, and we knew that by drawing the Lewis dot structure. Then looking at how many domains we had to figure out what shape it's in. So once we verified that it's a linear shape, we then look at both bonds. We have a carbon-oxygen bond on the right, and we have a carbon-oxygen bond on the left. And if I subtract my carbon and my oxygen, we see that those are polar bonds. My O is my slightly negative end on both sides. But look at this. Yes, I have two polar bonds, but because they are playing a tug of war in which the people, or we'll say the atoms, at opposite ends of the rope or opposite ends of this molecule are pulling with equal force, there is no net dipole moment. This would be a nonpolar compound. Let's look at water. H2O. I need to draw my Lewis structure. I would count my electrons. I know that oxygen has 6, each hydrogen is 1, so there would be 8. And if I drew O with an H on one side and an H on another, you might think, oh, well, that's a linear compound. But no, we know that oxygen has 2 lone pairs. And if I looked at my 1, 2, 3, 4 domains, 2 of them lone pairs, 2 of them atoms, we see that it is a bent structure. So it actually is looking like this. Once I know that, I can then look at my OH bond and my OH bond. When I subtract those two values from O and H, I see, oh, I have a polar bond. And I would point my arrow towards my oxygen end of the compound, point my arrow towards the oxygen end of the compound, and because it is bent, it is not an equal tug of war. So there is a net dipole. Because these are both pointing this way, I have a net dipole of a charge going in that direction. This molecule is polar because we can say this molecule is electrically lopsided. Here are 3 other compounds we can look at. BF3, again, if I looked at each of these 3 bonds, we would see that they're polar. And notice, they are pulling equal and opposite directions. They cancel each other out. So BF3 is nonpolar. There is no net dipole. Let's look at Cl2. CO. In this compound, now while it looks similar to BF3, the 3 atoms that are surrounding that carbon are not the same. So it is not an equal and opposite pull. We could subtract these 2 bonds and see that those are polar and this is polar, but again, they're not equal numbers. So there is a net dipole. When I look at NH3 and we subtract these NHs, they are all polar bonds, but what's different from that compared to this, these 3 cancel each other out. But ammonia, remember, for nitrogen to have that octet, has those lone pairs. Anytime there are lone pairs, it will be a polar compound. Let's look at these examples. CH4. Now we said earlier that the carbon-hydrogen bond was nonpolar. It is. They still put slightly positive simply because it's not 0. However, because I have 4 of the same H's around, they're all pulling equal and opposite. There is no net dipole. Here I have CH3Cl. So I have carbon with 3 H's and a Cl. Now this one is a polar bond, therefore it is polar. It's pulling in that direction of the polar bond. CH2Cl2, again, I have two nonpolars, two polars. So my net pole is going to be in between, going in that direction of those two poles. This one is going, we'll say, up and right. That one's going up. So it will go in that direction of those two poles. Here I have one hydrogen and three chlorines. So my net is going to be in this direction because I have pulling, pulling, pulling. They're not canceling each other out. Now here I'm back to, I have four of the same polar bonds. They're going to cancel each other out. So this is a nonpolar compound. Pause the video here and see if you can answer this question. If you drew these compounds by actually starting with the Lewis structure, then figuring out what shape it is, for NF3, you would see that it's trigonal pyramidal. We have those lone pairs of electrons. Anytime there's lone electrons, it's going to be a polar compound. And we can also see that we've got pull in this way, and down. So we're going to have a net pull going in that direction. For SF4, again, you needed to start with the Lewis structure to see what shape it would be in. Then I can go, oh yeah, each of those SF bonds are polar. So my net pole is going to be in, let's say, that direction. Pause the video here to see if you can answer this question. Yes, this would be a polar compound. The negative side is the fluorine atom because fluorine is the most electronegative in the molecule. So it's going to be pulled in that direction. They're not going to cancel out. If this was a chlorine, then yes, it would. But it's not. NH2Cl is going to be polar. Again, we have lone pairs. That's our indicator right there. So you would have to have drawn the Lewis structure to know that. And we would be pulling in the direction of the chlorine because it's the most electronegative. SCl2 is polar. We have two lone pairs of electrons, but we're also going to be polar in the direction of those chlorines. This compound is 1,2-dichloroethylene, and it can exist in two forms. What do you think? Are either of these planar molecules polar? Just by looking at them, what do you think? This first one is polar and the second one is nonpolar. Let's look why. CCl is going to be a polar bond, and this CCl is going to be a polar bond. C and H are nonpolar. So we have an overall pull. If this one's going down and right, this one's going down and left, I have an overall pull down. But let's look at this second compound. My polar bond is pulling this way, and my polar bond is pulling that way. Those are equal and opposite, and they will cancel each other out. So it is a non-polar compound overall. Pause the video here and try to draw this. Hopefully after drawing it, your Lewis structure looks like this. When you found your formal charges, we would have a formal charge of +1 on sulfur, -1 on oxygen, and a 0 on chlorine. It is trigonal pyramidal shape, and the molecule is polar. The positive end is on sulfur. This is my slightly positive end, and the negative end is on oxygen. Which one of these is polar? It would be ClF. N2 is a pure nonpolar compound. CO2, while it has polar bonds, remember they cancel each other out. It's a linear compound, so one's pulling this way, one's pulling that way, and they just cancel each other out. And BCl3, while it has polar bonds, that boron has exactly equal and opposite 3 polar bonds, so they cancel out. Which one of these is polar? It would be NCl3. There's going to be lone pairs of electrons, which is your big indicator, so you would need to draw it out. SF6, yes, they're polar bonds, but they're 6 in all equal and opposite directions. O2 is pure nonpolar because it's diatomic, and those 2 sulfur bonds are also going to cancel out because that carbon is going to be double bonded to that sulfur in opposite directions. Which one of these is overall polar? NF3 again. CH4 are all nonpolar bonds. SF6 are all going to cancel each other out. VEF2 is an ionic compound, and it's going to be linear. Again, so that polar bond is going to cancel out that polar bond because their tug of war is equal and opposite. So we're left with NF3. And the last join in for this section, which are the polar molecules? And you should get these three for our polar molecules.